can see my screen?
Yes.
So today the paper I'm gonna present is called GAN Lab, Understanding Complex Deep Generative Models Using Interactive Visual Experimentation by Min-Soo Kam et al. Basically, this is a visualization tool helping us understand how GAN network works, because last week there is one guy present the generative model. So this week I think I'm gonna present this paper. The reason they are making this program, this visualization tool, is because the rise of GANs and their uses. Synthesizing super resolution images is one use. Like we can take a low resolution image and use GAN to make it high resolution. Also the image to image translation, like this example here, we can see it takes a sketch and output a realistic image. And also all the apps we see, those are photo app, like changing age or changing your gender, things like those. They are all using GAN network. And currently there is no interactive visualization tools for complex models. The difficult part of learning GAN is understanding the interplay between the generator and discriminator. They are very complicated. That's why we need a tool to understand them. Their contributions is it's the first interactive tool to design for non-experts to learn and experiment with GAN models. And they have novel interactive visualization design. This is one of their manifold way with generator changing the grid. After the generator, the input noise become like a certain shape, which I will discuss. I will talk about it later. And they have this new interactive experimentation features, where it can visualize the training step by step and tuning the hyperparameters while training, during the training. And it's a browser-based open source implementation. It implemented using TensorFlow-js, so we can run this in our browser. We don't need a powerful server in the backend for every user to train the GAN model, which takes a lot of resources. And I will talk about the idea about GAN network, generative adversarial network. So a traditional GAN network has two main models, a generator and a discriminator. A generator takes a random noise vector, usually what we call Latin vector, as an input and generate a fake sample. And the discriminator takes a real sample and a fake sample generated by generator as input, and to tell if the input is real or fake. Yes? Somebody raise hand. Okay. Well, so yeah, this is the basic idea of GAN network. We can see in this picture, it described more clearly. So at first, we have a real data set, all our samples inside, and we have a generator which takes a random noise, usually 100 dimension vector or something, and it generates a sample as the same size of the same shape with our real data set. Then the discriminator will take both the real sample and the fake sample one by one, and to tell if it's real or fake. And yeah, the loss is used to back propagate to the discriminator and generator both to do the optimization. So we are training 2 neural networks there. The challenge is complex model structures with submodels. GAN has 2 submodels and usually multiple layers in each. It is crucial to find the appropriate levels of visual abstraction for the models. And usually when we are using GAN models, we are training high dimensional data sets. For example, images. Usually an image with 64 by 64 color image has 3 by 64 by 64 dimensions because RGB channels and the pixel. And many training iterations until convergence. The tool needs to keep providing users with information during training, and users should be able to provide feedbacks to models by changing hyperparameters. Conventional deep learning frameworks not fitted for multi-user web-based deployment. Their solutions is visualize high-level component with proper abstraction and using low-dimensional data set. In this tool, they are only using 2-dimensional data set for the visualization. For easier to visualize. And dynamic experimentations through direct manipulations of hyperparameters. And it supports step-by-step execution for learning the training process in detail. And deployment using cross-platform lightweight web technologies, which I already talked. It's using tensorflow-js running in the browser. This is their main interface. It has 3 basic components: the model overview, the layer distributions, and the matrix. I will talk about them one by one. So first, the model overview graph. Visualize model structure and the data flow. As we can see here, the data flow comes with first taking a random noise. In this case, it's a 2D Gaussian noise, and through the generator, which transform this random noise into the shape, a fake shape like this, which looks a little bit like the real data set here. And the discriminator take the real sample and the fake sample to justify if it's real or fake. And after this, it taking the loss, in this case, log loss back to the discriminator and the generator. So the data is, they are using 2D data set for better comprehension. And the real sample is showing in green color. It's a 2-dimensional vector. Each point is a 2-dimensional vector represent the location in 2D space. The random noise is represented in purple color. It can be, when it first generated, it can be either 1D or 2D. But after the generator, it should be the same shape as the real sample. And it can be both uniform or Gaussian. And this is the output of the generator. Output of the generator generated with random noise. For well-trained GAN, the distribution should look like the real samples distribution. That's the idea of GAN network, right? And this is the visualization of generator. It visualized the transform result as a 2D manifold. First, it generated a grid, a 2D grid, and each cell represents a certain noise range. After the generator, each 4 corners of cell by the generator returns their transform position, forming a quadrangle. So if, let's see the picture here. If this cell is here after the generator, it will be here and somewhere here. And it basically, it's morphing the shape of the 2D grid. So after the generator, it should be, it should how do I put it? Yeah, it should be the output shape of the generator. It's the mapping. It's the mapping of the generator. The discriminator is using the grid background color and grid cells to show the prediction values. The darker green for higher value, the points inside the cell are likely to be real. And the darker purple for lower the value, the points inside the cell are likely to be fake. As GAN approach the optimum, the colors become more gray, which means the discriminator cannot tell if the point inside the cells are real or fake. Take this as an example. So we know the discriminator will tell this part because it's purple. Most likely the points inside these grids are fake, and these part are most likely real. And between those, this gray area, the discriminator cannot tell if they are real or fake. This is what the prediction looks like. The prediction of the discriminator. If the so ideally, if it comes from real data, the output should all be green, right? And as we can see, there are still some outliers here because it's not well trained, and some of the real data still be considered fake. And yeah, still some fake data considered to be real. And this is the view of the gradients for generator. It's computed for each fake sample point by backpropagating the generator's loss. A gradient represents a vector visualized as a line starting from the sample point. The length represents the distance. It tells the sample point where it should move to. The gradient is passed to the optimizer, and the optimizer will tell the generator's weight to adjust, optimize the generator's weight. So next time it will be more accurate. And this is their distributions. They put everything in one graph so we can see how the points are moving toward, the fake points are moving towards the real points. And I have some metrics view here. First view is the loss for both discriminator and generator. So we can see that ideally during training, the loss should be smaller and smaller. And also the second view is that evaluating of how similar of real and fake samples are. It's using two divergence values, the KL values and the Jensen-Shannon value. They also support the direct manipulation of hyperparameters. Currently, they support number of layers for generator and discriminator, number of neurons in each layer, and also the optimizer type, SGD or ADAM, for updating the weights inside the generator and discriminator, and also the learning rates, the loss function, and the number of epochs for training, and noise dimension and distribution type. Here I have an live demo, so we can see how it works. Let's pick a distribution, for example, like this. If this is 2 Gaussian distribution here, and at first our noise looks like this. It's a 2D Gaussian. Maybe let's change to 2D uniform distribution and change to, let's keep the loss function as log loss. And if we run it, we can see first the random noise is not making sense. It's flying here and there. But during the training, we can see it's now 400 epochs now. But at the end, the data points, the fake points are moving towards the real samples. We can see the distribution is more and more like the real samples. And given it enough time, if the model is correct, it should give us a good result. So this is the basic idea of this tool. The limitation and future works. So now they have to transfer the user knowledge to higher dimensions. Like we say, GAN network for images. How would it work? Because if we only visualize the image pixel color, it doesn't make any sense. We cannot see how the generator works there. We just see the pixels being from random to real samples. And also the speed and scalability, because it's using JavaScript, so there are speed limitations. And supporting more GAN variants. Now it's only very simple 3-layer models. Later in the future, they might add more models there. This is all. Thank you. Do you have any questions?